Yep. All right, so the plan is. Oh my God, it's Friday. Do you pay attention at all? Seriously. All right. I know. I know. And listen, guys. I don't care if you pay attention or not, but then if you're gonna complain about not understanding things at the same time, you just look dumb, right? Like bad choice maker, like stupid in that regard. Not dumb because you can't learn things, but dumb because you make bad choices. Daniel, I'm trying to help you out here, my bud. All right, so. All this crap. Don't write anything, just watch. All the other classes had better luck when they watched, okay? And I think you guys, for the most part, did okay yesterday for those of you guys that were here. All right, so here's the general idea, okay? Here's the same triangle that's on this page. It's the same triangle, just bigger, okay? And I colored it. So here's the idea. We know that if two triangles have the same height, like this red triangle and this blue triangle, then their areas will relate the same way that their bases do. Are we cool with that? Right? When we put the areas over each other, the halves cancel, the heights cancel, and all we're left with the bases, right? Cool. Now, same thing here for these two triangles. This green triangle and this, purpley pink triangle. These two triangles down here both have the same height, right? And so they should relate to their bases in the same way. And I wrote it like this. Are we cool with that? Right? They should relate to A and B. These should relate to A and B. If you're not on the right page, that's okay.
I go get a drink.
All right. So, bases, we good? Now, we know from our first lemma that when we have three ratios equaling each other, we can take two of those, set them up like this, and they'll equal the third guy, right? Remember that from our first lemma? It looks kind of weird, but it's true. These two together. On the first page, right, it said we can combine these two and get the third. I just took these two and got that guy. We cool with that? Why it's true, maybe not. But that's our first lemma. We proved that. So I went from here to here. Are you digging that? That's our first lemma on the first page? Okay, cool. Now, we know what red triangle area minus green triangle area is. Here's the red triangle. Here's the green triangle. When I subtract that, I get the orange, right? The orange is what's left over. Daniel, put the phone away.
I'm looking up what it says.
Well, you can ask me that. It's also above on the page. You should have written it down. CV is any line that goes from the vertex to the opposite side. So what we're left with is this orange triangle. Same thing here. Blue minus pink. Blue triangle minus pink triangle gets us the yellow, right? Which I wrote in purple because I don't have a yellow pen. Sorry. So we know that this must be true as well. So these two triangles also go with these two bases. And that's kind of weird because A and B aren't a base of these two triangles, right? They're not a side of these two triangles. But because of all this matching height stuff that we get when we have a bunch of Cevians intersecting at one point, these two triangles will also go with these two bases. Are we cool with that? Do we see that sort of? I'm going to give you another opportunity to see it. Same triangle, but now I've highlighted different ones. Okay, same triangle. Notice our blue and our red triangle, blue triangle, red triangle. They have the same height, so they should be proportional to their bases, right? C and D in this case. These two are the same height, right? The pink and the green. Yeah? So they should be proportional to their bases. Awesome. So I've got red and blue equals C over D. And green over pink equals C over D. So I should be able to write that blue minus pink and red minus green is going to be these triangles, right? And they should be C over D. These triangles go with C over D as well. We cool with that? Yes.
Wait, so when are we going to grade our test that we were going to grade?
Friday. That was in the Google Classroom thing. So these go with C and D. We cool with that? All right. Same triangles. Different ones colored in. Blue triangle, red triangle, same height. So their areas should be proportional to their bases, EF, right? These two, same height. So their area should be proportional to their bases. So that means red minus green and blue minus pink is proportional to E over F. Well, what is red minus green? It's this guy, right? And what is blue minus pink? It's this guy. So these should be proportional to E over F. I'll say it one more time. Yeah?
So the triangles are what? All right. You're saying that the orange triangle has the same base as A? Or what? Proportion?
So the relationship between these two areas will be the same as the relationship between the bases. Okay?
Yeah.
So we know this to be true, right? Red triangle and blue triangle relate to their bases, right?
Yeah.
Green and pink should relate to their bases, which also happens to be A and B. From there I got this, which is our first lemma, and we know what red minus green is. It's orange. And we know what blue minus pink is. It's yellow, which I use purple down here because I don't have a yellow pen. Okay? So therefore, they must also be proportional.
Yeah.
Which is weird because those aren't, A and B aren't the bases of these guys, right? But it must be true through this logic. Now, the reason I did this is because we want to prove that this equals 1, right? So I need to know what A over B equals, and I need to know what C over D equals, and I need to know what E over F equals. Well, I found what A over B equals. It equals those two triangles, right? The area. And I found what C over D equals. It equals these two triangles. And I found what E over F equals. It equals these two triangles. Now you might notice, look at this triangle. I'm going to flip the page. This is my AB stuff, right? Don't I use that triangle again? This time for C and D? There's some overlap there, right? Watch this triangle. I'm going to use that again for E and F. Right? I use it for E and F. So there's overlap now. That means when I multiply these things together, things should start to cancel. And when things cancel by division, they end up being 1. So here's my logic. I know that this triangle and this triangle should relate to their bases because they have the same height. They have the red height, yeah? I know that these two triangles here and here should relate to their bases because they have the same height. Therefore, I should be able to write this, right? You with me on that? Cool. What is this minus this? Well, it's this triangle here. The big triangle minus this triangle is this triangle. And what is this minus this? Well, it's the big triangle minus this triangle, so it's that triangle. So these two triangles must equal A over B, which I wrote down here. I did the same dumb crap, ignore this. I did the same dumb crap with the other sets of triangles and got these guys.
So you can just say by similar logic.
Yep, by similar logic, by the same dumb crap, these leftover triangles must be C over D and these leftover triangles must be E over F. Okay, we feeling that? I just did it for all 3 sets. Again, what are those 3 sets? These two go with A and B. Sorry, let me get up here. These two go with A and B. Same dumb logic. These two must go with C and D. Same dumb logic. These two must go with E and F. Are we cool with that idea? So I wrote that here. By same dumb logic, these guys. It's alphabet soup. Don't worry about the letters, right? Those are just different triangles. I pointed them out to you earlier. So then when I multiply A over B and C over D and E over F, well, what is A over B? It's this. What is C over D? It's this. What is E over F? It's this. And you should notice ACG. ACG. What is area of ACG divided by area of ACG? 1. Anything divided by itself is 1. Area of ABG divided by area of ABG. 1. Area of BCG divided by area of BCG. 1. And what's 1 times 1 times 1? 1. And that's it. Now, it's weird because you have to see these triangles. But the good news is if you see it for one set, big triangle, subtract their bottoms, we get these, right? So that must be A over B. You do same dumb logic and get the other ones. Yeah, you have to write a lot of letters and you have to check which triangles go with what. These two go with E and F. These two go with D and C. And these two go with A and B. But after that, it's just multiplying them like they asked you to do and canceling to make 1. It's weird, and you shouldn't feel 100% about it because it's different. But notice, did we write by LPT, by vertical angles? Did we write? No. It's all by algebra. And then by same dumb logic, right? That's all it is. It's not impossible. It's just different, and you're not comfortable with it yet. So give it some time. That's the idea.
Is there like a shorter way to do this than writing like all those?
Yes. So here's me doing it again, okay? Big triangle and big triangle, go with A and B. Small triangle, also go with A and B. So I can subtract them, and they should be A and B. When I subtract them, what's left over? These two. Daniel, I'm answering your question. The question you asked, if there's a shorter way to do this. No, if there's a shorter way to do this. All right, we have to have a heart-to-heart. None of you, not a single one of you, is smart enough to do this on your own. Some of you, especially, this is especially true. Most of you figured out first semester you can't BS your way through this, right? There is no way. I'm hearing about other people talking about their finals. They got multiple choice, matching. Shut up and listen, okay? Right? There's no way in hell you're going to do this on your own. Daniel, you should be an A student in this class. You're not. And the difference isn't because you're not smart enough to pull it off. It's just because you're not smart enough to shut your mouth and pay attention. Hey, your boy's trying to help you out.
Are you an A minus?
Okay? No. I don't. I'm not calling him out, but like, okay?
Because you haven't graded anything.
Because you turned him in late.
In the warm-ups.
Because you turned him in late.
Yeah.
Yeah, you're welcome.
Well,
Should be zeros.
I turned them
Should
in
be zeros.
Like 2 weeks
So
ago.
my point is, Daniel, when you ask a question, at least have the common sense to pay attention to get the answer. Last time I'm going to go through it. 2 big triangles go to A over B. 2 little triangles go with A over B. By our first lemma, we should be able to take these two and subtract them in this weird way and still get A over B. So that means this triangle and this triangle go with A over B. Because what is big triangle minus pink triangle? Big triangle minus pink triangle? This guy, right? What is this? Well, that's just saying this minus this. So it's this. I wrote that down here, so they must go with A and B. I do the same dumb logic for all the other triangles. So these guys go with A and B, these guys go with C and D, and these guys go with E and F. Now, I made sure the colors matched up this time. We use this triangle twice, we use this triangle twice, we use this triangle twice. So when I multiply them, things cancel and I get 1. Okay? Before we go on to proving the converse of this, okay, I want to practice with this new technique for proof called proof by contradiction. The idea is this. It's really hard to prove that today is not Saturday, right? But I can prove that today, if it were Saturday, it wouldn't make any sense, and therefore Saturday must not be today. So let me say it again. It's very hard to prove today is not Saturday. But if I assume that it is Saturday, I can show you that that would be absurd. Why? Because students are here in school and students don't show up on Saturday. So therefore it must not be Saturday. We assume that it's true, and then show that it's absurd, so obviously the opposite must be true. I can't prove today is Saturday, or not Saturday, but I can prove that it would be absurd if it was, right? None of y'all will be here. So I'm going to go grab something for you. We're going to practice a little bit of proof by contradiction and do a little bit of math, okay? So hang on.
Dave, you like the zeros. You don't have like 3 tests. What? Right?
Alright, here you go.
Why do I need 30? I'm trying to blow my
I get it, but if I do that, I just do that.
Alright. So, practicing with proofs by contradiction. We'll start out with some simpler stuff. I know it looks kind of weird because you never had me for algebra, but I'll explain what the symbols mean.
Yes, exactly.
It's really not saying anything that profound. So this first one, it says, what we're trying to do is we're going to prove that 2 positive integers always have a positive sum. So what I'm saying is, think of 2 whole numbers, right? If you add them together, will they always end up being positive? Yeah, whole numbers are anything 0 and above, right? And we're talking whole numbers, so no fractions, right? So 2 numbers that exist in the whole number set. That's what we're saying. A and B are 2 numbers that exist in the whole number set. So like 1 and 2, 0 and 5, 6 and 11, whatever you want, right? As long as they're not fractions and as long as they're positive. So we're assuming that we have 2 whole numbers. Will their sum, when we add them together, always be greater than 0? That's what we want to prove. Now you look at this and you're like, well, of course, right? 3 and 4 is never going to be negative when we add them together. But how do we prove that for specific numbers? So what we're going to do is we're going to assume that it's not true. we're going to assume that this is not true.
But what if there's 0 and 0?
0 and 0, ooh, greater than or equal to. That's true. We should do greater than or equal to. We'll exclude 0 for now. We'll make it this set. Cross off the 0, make it a 1. That's the natural number set. I'd written out integers earlier, and I said integers greater than or equal to 0, and I thought that was too complex, so I switched it over at the last second to this. Good catch. All right, so assuming that these are natural numbers, right, will a and b, when they sum together, always be greater than 0? So we're going to assume the opposite. Assume a plus b is less than 0. Assume that it could be negative, right? Less than 0 when you add them together. Now we're going to prove that this is absurd, therefore it must not be true. Therefore the opposite must be true, right? So what I'm going to do is this. I'm going to subtract b to this side, right? What's 0 minus b? Negative b, right? Now check it out. We assumed a was positive, right? And now you're telling me that this positive number is less than a negative number?
Well, if B was negative at first.
Yep, but it wasn't. You know why? Because we know that a and b are both natural numbers, right?
Wait.
What's the
I didn't
Greek?
So natural numbers are anything 0 and above,
Okay.
right? Whole numbers, essentially, is what we're saying. So b and a, we know, start out positive. So when I move it over, it's negative, right? So you're telling me now that this positive number is smaller than a negative. Absurd.
What's the weird E Greek symbol?
Oh, the weird E? It means exists in this set.
What?
A collection of numbers. What collection is that? The natural set, right? All the numbers that are natural, like 1, 2, 3, the ones you count your sheep with. Again, you don't have algebra with me, so you're not familiar with these symbols, right? But it's okay. I'm just talking about positive whole numbers, okay? A and B are positive whole numbers. So I assume that this was true, that you could add two positive whole numbers and get a negative number, right? Something less than 0. Well, when I do that, I get this. That says a positive number is less than a negative. Is there any way a positive number can be less than a negative number? No. So this is absurd. We say this is a contradiction. You can write it like this. Absurd. Whoops. Absurd. Absurd. You can do this. You can do this. 2 arrows pointing at each other. Contradiction. You can do this as a contradiction symbol. Whatever you want to do.
Is that how you always write your arrows? 2 lines?
You have to for math. They're bolded. That's why. And I can't write in bold with a pen. So any of those mean absurd. Contradiction. Right? We can't have a positive number less than a negative number. Therefore, our supposition, the thing we assumed, must not be true. Therefore, the opposite must be true. So therefore, a plus b is greater than 0. And we're done. Does that make sense? It was really hard to prove that all whole numbers add up to something bigger than 0. So I assumed that, well, what if they couldn't? And we soon found out that would screw up all math. Therefore, it must not be true. It must be true that they do always add up to something bigger than 0. Are you feeling about 25% on this? I don't expect 50. About 25, Erica? 25-ish? Okay, say 25. Let's look at the next one. I think the next one will click for you better.
Well, this one makes a lot of sense.
Prove that the sum of 2 even numbers is always even. So think about it. Think of 2 even numbers. Add them together. Do you get an even number?
Yes.
Yeah, you do, right? And it's always true. Now, how do we prove this? We don't have to just say, well, it has to be, right? It's not a postulate. We can actually prove this. This is a theorem.
Because math.
So I'm saying, given that a and b exist in the integer set, meaning that they are integers, okay? So any number, positive or negative, that's a whole number. Does that make sense? So 0 and 1 are on the board, negative 1's on the board, 5 is on the board, negative 12 is on the board, right? But not fractions. Does that make sense? Every number other than fractions. That's what that means, okay? So why did I write 2a plus 2b? Well, I want 2 even numbers. How do I know that 2a is even?
Because no matter what you
2
put.
times that number will be even.
Yep. So the definition of even is we can divide it by 2, right?
Yeah.
What happens when I divide that by 2?
You get.
I get a, right?
Yeah.
And a is a whole number, which means I can divide it evenly, right? If I got a fraction, right, you take 5 and divide it by 2, you get a fraction, right? That means it's not one of these guys, right? It's not a whole number. So if I divide this by 2, I get A, which we said was a whole number. So it divides evenly, right? Same thing with B. This whole thing must be even as well. So we have 2 even numbers, and we want to prove that when we add them together, they end up being even. So here's what I'm going to assume. Assume this, that they add up to another number, C, right? They add to something. And let's make C odd. Let's assume they don't add up to something even. Let's assume that they add up to something odd. Now, how can we prove that this is absurd, right? Well, here's what I'm going to do. I'm going to pull out a 2 from both of these. And I'll pause for station identification. Everybody cool with that? I pulled out a 2. Right. Now, we assumed C was odd. And to be an odd number, right, that doesn't count with fractions or anything, right? Like 1 would be an odd number. Is 3/4 an odd number? I don't know. I mean, no, right? It's only whole numbers that we can say odd or even. So C is odd. Now I'm going to do this. There are 2 cases that C could be. Case 1, C over 2 is not an integer. Meaning that when I divide C by 2, I get a fraction. Does that make sense? Right? So either that's a fraction that can't be simplified, right? Like 5 over 2 or 7 over 2, right? But here's the problem. If this isn't an integer, didn't I add 2 integers together? Think of 2 integers. Whole numbers, basically. Add them together. Do you get a fraction? Think of 2 integers, like 1 and 5. Do you add them together and never get a fraction? No. So either this isn't an integer, meaning it doesn't divide evenly by 2, right? And it stays a fraction like 5 halves or 7 halves, right? But I got a fraction from adding 2 whole numbers. Not possible. This is a contradiction. How could I get a fraction from adding 2 whole numbers? Or it's even. Let's write it like this. C is even. Because if C were even, when you divide by 2, don't you get a whole number? Right? But if C is even, what does that contradict? Our assumption that C is odd. So this is a contradiction because we assumed C was odd. So is it possible for C to be odd? No, because if it was odd, we would get a fraction, and you can't add 2 regular numbers and get a fraction.
Contradiction next to C is even.
C, if C were even, it would contradict what we said up here.
Oh.
Therefore, our assumption must be wrong. Therefore, C is even. So we assumed C was odd, and we proved that that would be absurd. If it was odd, we'd get a fraction here, right? When you divide by 2, it wouldn't come out evenly. And we have 2 regular numbers adding up to a fraction. That doesn't make any sense, right? Or C is even, and it comes out nicely, right? But if it were even, it wouldn't be odd. So that contradicts what we said earlier. So C must be even. That's only one way to make it work. 2 numbers that are whole should always add up to a whole number, right? And if we divide it by 2, the only way it'll be whole is if it's even. So it must be even. So the reason I'm showing you this, open up to page 5. It's the page we haven't done yet. We're going to prove the converse of Ceva's theorem. And we're going to prove it by contradiction. So remember, Ceva's theorem says if all of the Cevians are concurrent, then we get this relationship, right? They all equal 1. The converse says if all those equal 1, then the Cevians must be concurrent. So if all these equal 1, then this must be concurrent, these 3 lines. So we're going to assume the opposite. We're going to assume that the Cevians aren't concurrent. So we're going to write that. Assume AE, BF, and CD are not concurrent. Assume they're not concurrent. Well, if that's true, there should be a line that exists that we can draw from C that does intersect all of those. I'm going to draw a line like this. And we'll do it X. Okay? So if these three don't intersect at a point, there should be a line that does. Does that make sense? I'm going to say it's this line. I'm going to say that line actually does intersect through the middle. The other ones don't. This one right here doesn't, but this one does. Okay? Cool?
I drew the X.
Okay. Wait.
X is the point.
Concurrent means that they intersect at the same
At one point, yeah. So
don't
these
they
three
already?
lines, they look like they do.
Right.
I'm going to say, assume they don't, right? Then there should be a line that does. Let's call it this line, right? It could be any line, right? Let's call it this line. So we're going to let CX exist and also let ADXB exist. All that means is that we have two lines that intersect at X, right? Are we cool with that? That tells you that CX exists and that X ends up on this line. Are we cool with that? Right. Cool. So by Ceva's theorem, then we should have that this part right here over this part here should equal this over this equal that over that, right? Because those three are all concurrent. I said that this blue line and those two lines are concurrent. So I should have that whatever AX is, the distance between here and here, and XBR should equal, let's call it C and D, just little c and little d, and little e and e, little f. And that should, when we multiply those together, sorry, multiply. When we multiply those together, we should get 1. Right? By Ceva's theorem.
Oh, that's
Yep. Which we proved, right? We proved that earlier, so we can use Ceva's. So by Ceva's theorem, this should be true, right? If those are concurrent, then I should be able to say this. These are dots, multiplication. But here's the problem. I know that AD over DB times C over D times E over F equals 1. AD and DB, right? Because we're assuming that it does. But here's the problem. In order for this to equal 1 and this to equal 1, right? Since they both equal 1, they should equal each other. Are you down with that? So they both equal 1, so they equal each other, right? Now, what happens when I divide both sides by E over F? I divide this side by E over F, I get 1, right? And I divide this side by E over F, and I get 1. Got to do it to both sides, right? I'm going to divide both sides by C over D. What do I get? Anything divided by itself is 1. I do it over here. Anything divided by itself is 1. So, therefore, AX over XB equals AD over DB. So that's telling you, I'm going to zoom out a little bit, that's telling you that this length here, AX, is the same length as AD. Right? And the length XB is the same length as BD. I'll highlight that. It's telling you that these two lengths are the same as these two lengths. That AD is the same as AX. And DB is the same as BX. How is it possible to have lengths like that be the same? It's not, right? If you cut a board in half, right, here's a board. If I cut it in half, well, there's one way to do it, right? Right here, at this point, right? Show me another way to cut it in half. That's not using that point.
vertically.
Vertically? Well, okay. We're pretending that this board has no width, you dummies. All right. That was good. And it's horizontal, is what you meant.
Oh, yeah.
But yeah. But I knew what you meant.
Same thing.
Well,
Yeah.
it depends how you're holding the board.
Is there another way to cut this board into two equal pieces? No, there's only one midpoint, right? So however D cuts AB, right? There's only one way to do it. Maybe it's like 2/3 and 1/3, I don't know, right? But you can't have this also be 2/3, right? X can't also cut the board into 2/3 and 1/3. So it's a contradiction. Therefore, AX, or we should say that X and D are the same point. Well, if X and D are the same point, then the lines must be concurrent. Right? We said that X was either going to be concurrent or D was going to be concurrent. So if they're both the same point, they must be concurrent. So our Cevians must have been concurrent to begin with.
So can we do this on any of the problems on the test, or will it tell us which one to do on each?
Proof by contradiction?
Yeah.
This is the only one you'll need to do proof by contradiction for so far. Yep. So we have a contradiction. How can X and D be different points when they equal each other? Right? I'm thinking of two numbers. They're different from each other, but they're also equal. What? Right? That doesn't make any sense. I can't have two things that are equal also be different. So X and D must be the same. And if X and D are the same point, then all our Cevians are concurrent. Cevians AE, BF, CD are concurrent. So what we did is we assumed that the Cevians weren't concurrent, which allowed us to say that, well, there must be some line that is concurrent with the other two, right? I'll make it. Well, by Ceva's theorem, since they're concurrent, I should be able to say this. But I also know that this is true, right? Because they told us A over B times C over D times D over F is 1. And what is A and B? These two guys. Do you see how this right here is A and that's B? Right? They gave us that. They said that had to be true. Well, if this is true, and we know this is true by Ceva's theorem, then they should equal each other, right? Because they both equal 1. And then this must be true. But how can you have two different things equaling be equal? Is that, you see what I'm saying here? AX over XB equals AD over DB.
Identical.
Well, how can two different things be equal? They can't be. It's contradiction. So X and D must be the same thing. Must be the same point. So therefore, our Cevians must be concurrent. Now, all Cevians aren't concurrent, right? You can draw 3 random lines in a triangle and have them not be concurrent. But if this relationship's true, then they must be. They must be concurrent.
So
I'll run over it one more time. What's your question, Noah?
is this the only problem that we can use this on?
You can use it for lots of problems. Some problems only have a proof by contradiction, though.
Oh.
This is another tool that we have in our tool belt to solve it. This one, the easiest way to prove this was by contradiction, and that's why I brought that tool in. The easiest way to do it is to prove that it would be absurd if they weren't, right? We'd have 2 points that are different but the same. Doesn't make any sense. Yes.
This is a great way to memorize.
Not all problems can, but some problems can only be solved by contradiction. How would you know? Well, it's just like anything. When you're trying to prove something for the first time, you get a problem. Like I give you guys a warm-up, right? And I say, figure out the proof, right? There's lots of different things you can try.
Rest in peace.
Do you know how to go about solving it? Not necessarily, but there's things you can try and you can get more information about it. Okay? So one way to do it that people have found is this. Are there other ways? Sure, but they're more complex and they require higher levels of algebra and mathematics that we're not into yet. But this is how we do this one. That's how I would show you to do it. Right? When I give you those proofs on a quiz, sometimes there's multiple ways to do it. Right? Some of you guys come up with different answers, but in general, the same basic concepts there. This is a different way of doing it, so a lot of the concepts that you'd use for a regular proof wouldn't show up here, right? But it's valid. Checks out. In order for all that to be true, for both what we assumed and for what they gave us to be true, then we'd have to have 2 different points that are different and the same point. And that doesn't make any sense. And so therefore they must be concurrent, because X and D must be the same point. So we drew a line and said it was concurrent, and it ended up being the same line as CD. Had to be the same line as CD. So if this line's concurrent and CD's the same line, well, then CD's concurrent, which means all of our Cevians are concurrent. All right, I want to take a break there. That's kind of a weird one, right? The story of this packet is that things are not necessarily impossible, they're just weird and take some grappling with. Getting used to this is important. I want you guys to practice this. Remember, tomorrow we are grading our quizzes in class, right? Which means if you wanted to take your one shot to finish that quiz, you need to do that today. If you haven't done it already. If you have a class period, like you guys have 7th period, right? You can come in during any time. I don't care if I'm teaching. Sit in the back, work on your quiz, okay? Please do that. It's much easier than having to wait till after school and none of you guys have time, right? Please come on in if you've got a study hall or something. Or if you have a teacher that's like, we're not doing anything today, or if they have a sub or something, right? Ask if you can come in here. I don't care if you do that on a regular day. You're like, man, I didn't get 3rd hour geometry, but I have a free hour 4th hour. Come on in, sit and watch the lecture again, right? Cadence 6. Before we go, I want to give you a add-on to the back of your packet. The last 2 pages are screwed up, right? Page 7 and page 8. Let me grab that for you. We're going to add on more to this packet next week. This was the first half of it. Tomorrow, we'll grade our quizzes and get into this last bit. I might start it today if we have a little bit of time. I don't think we do.
You stop. What would this be doing?
Daniel, I just explained. Replace the last page of your packet with this. The last page of the CD's packet. One of the do this. No. Replace the last page of your CD's packet with this.
Yesterday, I think this might be it.
Yeah, take it. Go ahead. I don't have that. Yesterday, Zayden taught 4th hour what you guys learned in 3rd hour from Cheyenne. I gave him, I believe, 6 self-development points for that, sitting for Cheyenne. It was great that they were able to help me out last minute like that. I appreciate that. I think those of you that paid attention to Cheyenne got something out of it. My 4th hour is much better at paying attention on the whole and did really well with Zane. I will tell you how many self-development points you have. I have not looked at the back yet, the ones you did for me on Wednesday when I was absent. I'll add those in this weekend. But right now, here's where this class stands on self-development. You need 20 by the end of the semester. Alex, you have 0. Ellie, you have 7. Chloe, you have 6. Zayden, you have 13. Peyton, you have 4. Jessica, you have 4. Why did I call you Jessica? Xavier, you have 6. Landry, 8. Erica, 4. Noah, 0. Andre, 0. Luke, 4. Danny, 0. Nancy, 6. Evan, 8. Coda, 4. Autumn, 0. David, 6.
Wait, what is it for?
Self-development points.
Like
Is that for the semester?
Yep, you need 20 for the semester. Okay?
Wait, how much do I have?
I've been in here like
Evan, you have 8.
17, because I put here it's
Matt, you're tripping.
8.
Okay.
Okay? What's up?
Yeah, but I've been in here 10 times.
Did he come in with you and actually do stuff?
I've been in here 3 times.
Yeah, that's an account.
What? I've been in here once just
Do you
messing
get
around.
self-development
I don't like this.
I'm sorry, hold on. Guys, I can't hear Erica. What do you say?
Do you get self-development
I've had 3 pencils broken these past 2
Ooh, that's a good point. I don't think I did that when you guys came in. 2 of you came in. I'll add on 2.
Thank you.
Yeah.
I was in homeroom.
So Landry, you have 8, and Erica, you have 6. Okay.
Oh.
Now, whatever you've done in the back when I was gone on Wednesday, I'll count that too. I just haven't gotten to it. What? Good idea. Whenever you do that, you get 2 self-development points, unless you've done it more than twice a week. Right? If you do it a 3rd time in 1 week, I don't count that. But the first 2 times you come in a week, I do.
Wait, you come in twice a week and you get it.
You get 4 points max for coming in twice a week. If you come in 3 times, I don't give you another 2. But you know what I mean?
I've been in here
I don't want people coming in 5 days for the first 2 weeks of a semester and being like, got him. Right? We're not doing that yet.
Actually, doing stuff I've been
I think I got this, so probably didn't. How do you want me to turn that
I
in?
have 10 because I came in.
I thought you meant you had 2 more back. Never mind.
Right here. I'll write SD at the top. And I'll check it out when
How much do we
put it in the mid.
How much do we need to get 10 or 20?
20 per semester. 20.
Wait, don't you get warm-up points for
Do it.
making a warm-up?
As long as it's not going to
We
get
need
in
to
trouble.
fix this right now.
Wait, so
Right?
I self-help. I self-help.
Why?
Because I came in here twice and actually did work.
What were you doing? Walk me through it.
why are you so
The first week I came in here with David, we did the.
That is
It was just
ridiculous
us.
how math works.
That's
What'd you do?
solid math.
It was like the
Mr.
first
Matt.
quiz or the second quiz. Went over the
Matt.
review.
It's very good.
This is
Because we
not
both failed
solid
it.
math.
I'll give you 4.
You
Wait,
failed
Mr.
Mr.
Mac.
Mac. I have a very
I think so.
I'll give you
I
4.
was gone.
What?
This
So,
is not solid
This is
math.
how it works, right? The thing we just learned, she says is right. If you have a penguin and you want to prove that they can't fly, by contradiction, you throw it in the air, when it falls down and dies, then you proved it, right?
Is that right? What? No, it's not. Is it?
You want to prove
So
penguins
what?
can't fly,
And then you
throw
say
You
that
assume
as
they
soon as
can.
chuck it in the air,
right?
falls
And when
down
they
and
don't, you
dies.
prove that. Yeah. That's by contradiction.
Math.
Good example. Math, right there.
Yes.
What if it was just that penguin?
Ooh, good point.
Fine,
Yeah, you need to
I'll
prove it
throw
for any
25
penguin. You need a
penguins in the air.
variable penguin, right? That stands
25
for
in the
all
air.
penguins. No, that doesn't work. There are infinitely many penguins you can check, so you have to prove it for all penguins,
100 for each species.
I will
right?
throw
Is that good
every
enough?
penguin
No.
on the planet in the air.
If you've proved something for the first 1,000 numbers, it doesn't mean that the 1,000th one it won't be true, right?
Okay, I'll randomly select one
And you'll have a
penguin
good
out of every group
idea,
of penguin.
but it won't be proven. You'll have a good idea.
But I can't say the average penguin can't fly.
Ooh, there you go.
See,
That works.
No.
yes.
By contradiction.
See, it's math. That is exactly how
For math, makes sense.
It totally makes sense.
If you want to
They'll
prove,
be dead, so it doesn't matter.
All right, tomorrow we're gonna grade the quiz rather quickly. Make sure you come in here and finish it up. That way the grading is very easy because you got most of it right.
then you throw
By the way, those of you that are studying for this quiz to finish it up, you know that the two weird ones, the circumcenter and the incenter, the ones that have the circles, go with the angle bisectors and the perpendicular bisectors. So angle bisectors form the incenter. Perpendicular bisectors form the circumcenter. The other two are super easy, right? Medicenter medians, right? Or centroid, right? And then the orthocenter orthogonals, right?
That might
Study
help.
up and fix
That
it.
might help.
That's really it, right? And if you know you have the incenter, well, the angle bisectors make it. So you must have angle bisectors somewhere. Draw them in,
One's right at it.
right? If this is the incenter, then you know you've got angle bisectors here, here, and here.
We're going.
Wait, what are all the stuff that?
Right?
Yeah,
Mr.
Mr.
Mac
Mac passes.
For semester.
And if it's the incenter, there must be a circle that reaches from here to here.
Wait, who do you have for study?
What, Mr. Wright?
You were for
Well, we do it so he actually believes it.
Wait, yeah.
What you should do is walk up and get super suspicious. Dude!
You guys are in the same class, right?
Yeah. I need to get a board. I can take it. That's fine. I'll just put it here. No.
What happened here?
I can't have everything.
Humidity changed a bunch over the weekend, and it exploded.
That's not everything from this semester.
Yeah, I know.
Glue was not strong enough
I
to hold the
don't-
humidity changes. The wood warps, right, over time, and it popped off.
That just sounds so.
So I gotta fix
Yeah.
it.
Someone told me I was supposed to like get a thing that you put inside the guitar so it stays like humid or something.
Yeah, you can do that. Now, if you keep it in a house that has the heat on constantly,
How do you know my middle name?